I mean, it might be worthwhile to look at what the calculator gives you. So let's just do a solve. So let's go into the calculator. Let's go to menu, to algebra, to solve. What is that? Menu 2-1. Is algebra the second menu? 3-1. Menu 3-1. That's going to be a good thing to know this year. Menu 3-1. Right? Menu, algebra, solve. And then type this in, and then don't forget comma X at the end. Right? So menu, algebra, solve. Type this in just like this, comma X, inside the parentheses, yes. The comma X goes inside the parentheses.
That's cool.
Now, does it give you this? I'm guessing it gives you the one that's up on the board, the screen over here. Does it give you this version? Okay. They are the same. The difference is, on this problem, I moved the XLN5 over here. On the one up on the paper up there, I did it the other way around. I moved the 2X over to this side and moved this over here. So all the difference is if I pull out a negative on the bottom and then cancel it with that negative on top, that's how you get the one over there. They're the same. Okay? Remember the old Algebra 2 problems where half the class would work it out and get half the class would work it out and get this, and the other half of the class would work it out and get, right? Because they got the X in one. Some people got the X on the left side, some got the X on the right side, but you still end up with the same answer, right? Because this one's negative 12 divided by negative 3, this one's positive 12 divided by positive 3. That's what's happening. Okay, same thing. All right. So we are going to get in. We're not going to go through and work all these. Maybe what we'll do is maybe I'll scan this answer sheet and post it online. I'll have it available if you want to look at it. Maybe over the next several days, maybe we can pull this out and work a few of them. Have some work time here at the end of the period. Maybe you can look at some. There were a couple I wanted to comment on, though. Here's 16. Just some of these algebra things that you see that are a little different, a little out of the ordinary, like e to the 2x. Well, that is e to the x times e to the x, right? E to the x times e to the x, you'd add the powers. So x plus x would be 2x. So this is really a FOIL. This is just a FOIL problem, right? Get e to the x equals 2. Get e to the x equals 1. Do the log of both sides. You get x equals ln2. You get x equals ln1, which we always should know is 0, so we just should put 0. So we just stop there. Now I went ahead and got decimals. If you were using a calculator, you know, you would get those decimals. But if you were using a calculator, you wouldn't even have done any of this. You'd have just done a solve right away. Yeah. But anyway, so ln2, that kind of stuff. Trig 1, 17 is kind of what I would call more of a basic trig 1. We're going to get into that on our next quiz. There's going to be some trig solved that we do. We're going to do some F primes. We're going to be chart kind of problems, just like the quiz yesterday. Be some chart kind of problems, and then you're having F prime, set it equal to 0, and you have to solve it. And when you solve it, it might come down like this, and you get sine x equals half. Well, where's that happen? Well, now my triangles are a little different there. I didn't do unit circle numbers like 1/2 or 3/2, but I did kind of the old geometry numbers, 1 and root 3 and 2, that kind of thing. But it's same business. So where is sine equal a half? That's at pi 6. So you either need to know that from the unit circle, or you need to be able to draw a 30-degree triangle and do SOHCAHTOA or whatever. And I've got a trig review video up online if you want to go watch that. If you want to come in and get some help on some trig stuff, I'd be glad to work with you on that. But where is sine positive? Well, that's in the first and second quadrants. So it's pi 6, 5 pi 6. Now, the directions didn't say to only go from 0 to 2 pi. So you guys probably remember this last year, right? So you could go around and around. I mean, really, think about this. When does sine equal a half? Well, if you think about the sine graph, and I apologize those people, if you're listening on the video, you don't get to see this right now, but, well, at least that part. I'll let you see this part. So sine, where does sine x equal a half? If you think about the sine graph, right? When does sine x equal a half? Well, there, right? There's an infinite number of times when sine x equals a half. This one happens to be at pi 6. This one right here happens to be at 5 pi 6, right? Both of them happen before pi, first and second quadrant. But then you got another one that is 2 pi from that one. And then you got one that's 2 pi from that one, right? Plus 2 pi, that's that cycle, the period, right? So every 2 pi, you're going to get another one. And every 2 pi from 5 pi 6, you're going to get another one, right? And so that's where the plus 2 pi n comes in. So add a 2 pi, add another 2 pi, add another 2 pi, and so forth. Then negative, subtract 2 pi and go back. All right, so usually we give you a limit. Usually we say between 0 and 2 pi, and then we're only interested in those. Okay, when you get down to this one, like 19, we could factor out a sign and then solve each of those. Where does sine equal 0? Well, that's at 0 and at pi. So I got 0 plus pi in. So 0, pi, 2 pi, 3 pi, 4 pi, and so forth. And where does sine equal -1? That'd be down at 3 pi halves. And then around again to 3 pi, 2 pi every 2 pi. This one's just pi in, though, because sine is 0 both at 0 and at pi. And then at 2 pi, and then at 3 pi. So those are just some things there. But like I say, this one, now this is an interesting one too. If you solve this on your calculator, it's got a whole bunch of solutions. I mean, so we'll talk more about some calculator ones later on. I don't know that we're going to mess with much of the calculator ones before next week's quiz, just because I would like to wrap this up and get a quiz in before Thanksgiving. And so what that'll mean is I'll probably cut out some things. I don't want to rush to it, so I want to give us time to, to talk about. So I'll try to pick as much stuff as we can, reasonably expect to be able to do before next Tuesday. And the one thing we might cut out for right now, we'll pick it up later, would be calculator solving and some of the issues it brings up. Okay, so we'll focus more on some no calculator solving. Okay, let me see. I think there was something on the back or on the front that I wanted to look at. Okay, on 5. Sometimes the best thing you could do is FOIL it out and gather terms together. So on 5, you really just needed to FOIL that out because you want to set it equal to 0. So you really need to FOIL it out, move that x over, and then you can factor some things. Okay, so FOIL it out, move the x over, then you can factor. This is number 6. Number 6 is a technique that we will use a lot, actually. Yeah, you could FOIL this, and you could FOIL this, and group terms together. The problem is you're going to get an x cubed, and it probably won't be something you would then be able to factor very well. So on this one, you'd want to look at it and say, hey, I got 3 of these and 2 of these. I can factor out 2. It's kind of like an a cubed minus an a squared. You can factor out an a squared. So we're going to factor out an x minus 2 squared. You don't have to use square brackets, but when I'm doing ones like this, I kind of like to set that apart. So that leaves me 1x minus 2 here, and then if I factored all that out, there's just a 1 there. So then that turns into x minus 3. You'll see when we get into derivatives how this comes into play, this kind of factoring here. So this is an algebra technique that's pretty important to us. And then it's pretty easy. Then when does this equal 0? Well, at 2 and 2 and a 3. Okay. 8 did not factor, so that's a quadratic formula one. Now, do we have to use a quadratic formula? Not very often. But sometimes in the AP test, the multiple choice question, sometimes you may get something where you got to remember the quadratic formula. So it's negative b plus or minus the square root of b squared minus 40c all over 2a. Or you can sing it. Yeah, it's Pop Goes Louisa, right? I'm not going to sing it.
I didn't learn that until I was in Mrs. Payne's class.
Mrs. Payne, yeah, I pulled it up from my Algebra 1B class the other year. They thought it was dumb, much like everything else. But, oh, that's not true. It shouldn't be so hard. All right, and this one turns out to have a negative inside the square root, which means there's no solution, right? It'd be an imaginary number, right? The old I, square root of a negative 1 is I. But there's no real solution to that one. Which, if you think about it, look at this. You know, since now, hopefully in this class a little bit, you might even think of this as, you look at this and say, that's a parabola, and with everything positive, with the plus 3 as a shift, and all positive, that's a parabola that's above the x-axis. So when you're saying, when does this equal 0, it kind of makes sense that it never equals 0. It never crosses the x-axis. And that's exactly what it is. It's a parabola that opens up, that's above the x-axis, and so there's no solution. Okay, last one for today. Number 10. Okay? This is that thing with clearing the fractions again. If I multiply everything by 2x, that's the simplest way. Now, you could get a common denominator over here and put them together. All right? And that's legitimate. That could work. But if you multiply both sides by 2x, the 2's would cancel here, giving you x squared. The x's would cancel here, giving you 4. Multiply this side by 2x, you get 4x. Group your terms, and then it turns out it doesn't factor, so that's another quadratic formula. Okay. So we got trig solving, we got exponential and log solving, we got algebra solving. You know, just things that are going to come up that we need to be able to do. It's not, you know, they're not going to be horrible solving ones usually. Usually the really messy ones are on our calculator. So, probably the trig ones are the ones we probably need to work on the most. All right, I will scan this and I will post it online under the documents and under today's notes. So if you want to look at that. All right, let's take a look at section 6 in your book. We're actually going to look at section 6 and section 7, and what we're going to do is we're going to start constructing our list of derivatives, of derivative rules. Now, this will not be the definitive list. I mean, if you want to start this kind of on a clean sheet of paper and whatnot, that's fine. You know, we kind of keep adding to it, and then we're going to later we're going to change the way we write them a little bit as we learn some new things. Some things will change. At some point, I will have a copy of the list to give to you as we kind of get it more complete. But that's more into chapter 3. So for right now, we just want the beginnings of kind of our derivative rules. And there'll be a part of our next quiz that will involve doing some derivative short with these rules. We had a couple on the quiz yesterday, but not too much. All right, so probably the first one I'd want to write down here would be some of them that we talked about with shifting and stretching and so forth. So one that is a very useful one is that if I'm going to take, now remember this notation here just means the derivative with respect to x. So this just means a derivative with respect to x. And if my function looks like this, so if I got sine, a power, whatever f is, if I have a number setting in front of that function, what do I do when I do the derivative? What do I do with that number? It just sits there and multiplies times the derivative, right? If I have 2 sine x, what's the derivative of 2 sine x? 2 cosine x, right? So if you multiply by a number in front of a function, and do the derivative, that number you're multiplying by just sits there. Because what it is a vertical stretch. So if you stretch a function, you change the slopes by that same amount. So we got to multiply that same number times the slopes. Okay? Another rule we had was if you shift a function left or right. Oops. If we shift a function left or right, does that change the slopes? But it does shift them left or right. So the derivative will have the plus or minus a in it as well. So this was one of the things I told you. As I said, the inside will always stay the same. Whenever we're doing a derivative of a function, we follow the rule, but whatever's on the inside always stays the same. Okay, so if it's sine x, it'll be cosine x. All right? If it's sine x minus pi halves, then it's cosine x minus pi halves. The inside always stays the same. All right, and then the last rule we had regarding this was if we have a number on the inside, like a k, multiplied times the x, some constant. What do we say we have to do there? Stays inside, but we also have to kick it out and multiply it times the inside, because that k is a vertical shrink. And if you are a horizontal shrink, or compress, or stretch. And so when you do that, you change the slopes. You change where they are, so that's why it stays on the inside. And you also change what they are. Their slopes get steeper. So you get k times f prime of k times x. So the k would stay on the inside, and you also have to kick out and multiply it times the k. So if you had sine 2x, the derivative is 2 cosine 2x, right? The 2x has to stay on the inside, but you kick out a 2 to the outside. Okay, so those are the rules we said with shifting and stretching and compressing and that kind of stuff. All right, so next rule. I ran out of room, you just keep right on going. So then we had our power rule. Okay, and this probably isn't the order we learned these, but this is how we write. So if I have an x raised to a number, then the derivative is the number down in front and the power decreased by 1. Right? And then we had our kind of interesting one that we talked about, which was e to the x. The derivative is e to the x. Now, I want to take a quick little side trip here. Don't write any of this down so you can rest your writing utensils. And I would like to do that derivative the long way. Which would be this, right? I'd like to do this derivative by the definition. We've already talked about how it makes sense. If we draw the e to the x graph, the y values get bigger, they're positive, the slopes get bigger and are positive. And sure enough, the y values are the slopes. Very interesting. Only function where that happens. Except for y equals 0. Right? All of its slopes are 0, all of its y values are 0. But that's a trivial example, I think. So really, the only real function where this happens. So what would that look like doing it this way? Well, tell me what this part would look like. What would f of x plus h look like? E to the x plus h. What would f of x be? E to the x all over h, right? Now, let's see if there's any algebra we could do to that. Oh, I forgot this is as h approaches 0. Obviously, we can't put a 0 in for h because we get e to the x minus e to the x. We get 0 over 0, so we want to keep going. So what algebra can we do? Well, it doesn't seem to be anything really, but there is. What causes you to add powers? When you multiply. So wouldn't it be true that e to the x plus h, wouldn't that be equal to that? Correct? E to the x times e to the h, you would add the powers, you get e to the x plus h. So let's do that. And again, this is limit as h goes to 0. Now what can I do up there? I can take out an e to the x. Right? Now this is the limit as h approaches 0. Okay, so now we got to look at something here. So as h gets closer and closer to 0, what happens to e to the x? Nothing, because it doesn't have an h in it, right? If h is getting closer to 0, e to the x is unaffected. It's just e to the x. It's not going to be affected at all. This piece, though, will be, right? So this piece is changing, and then times this piece, which is not changing, right? So what we can do with that, a little rule of limits that we don't have to worry about too much right now, is I can actually take this e to the x outside of that limit, because that is unaffected by h getting closer and closer to 0. Okay? So I can rewrite this as this right here. Now again, that hasn't helped me a whole lot, because as I plug a 0 in for h, e to the 0 is 1, 1 minus 1 is 0, 0, I still have 0 over 0. And I can't get the h's to cancel. But get on your calculators, let's do this as a calculator limit. And let's do a table on this guy right here. So go ahead and take the red piece, right, and do like we did on our tables and like we did on our quiz the other day. Type that into your y equals and graph it. Except don't use h, you got to use x. And then go to a table. And tell me what's happening as h, or x in this case, is approaching 0. Is it? Are you sure? This minus 1 is not up in the power. Don't put that minus 1 in the power. Just e to the h and then minus 1. So I think it's approaching positive 1, isn't it?
Yeah.
On both sides? Okay. Now is it 0.999 on both sides, or is it 1.01? So one, it's a little below 1, one it's a little above 1, but it seems to be approaching 1, which doesn't surprise us, right? So look what that means. So this piece, the limit is 1 times the e to the x. There, it worked out. We had to cheat a little bit by looking this limit up on our calculator, but okay, we couldn't do algebra all the way, but there it is. So it actually worked out. Okay, it made sense that it seemed like it might have its own derivatives, but it turned out that sure enough, it did. Okay, so I just think that's kind of neat to see. Yes? It's not that it doesn't work out on paper, it's just that our algebra techniques of factoring and common denominator stuff don't work on this. There's no algebra technique we can do to simplify this. Now, there are some other techniques that I don't really want to go into for how we can do something like this. They're just not important for us.
If we really wanted to.
If we really had to, we could. Right.
So you don't say that we're not smart enough?
Yes, look at his face.
Yes, let's go with that. The real answer, of course, is I'm not sure I know how to do it. So that's the main reason we're not going to do it. But because I think there's somebody smart enough to do, but it's not me. So we're going to go right on. So we're going to go on. All right. So anyway, we can be reasonably convinced that that derivative is that. All right. Now let's add a new one to this list. Now this is the section. This is section 2.6. 2.6 is about exponential. Let me talk to you a little bit about the rest of this chapter. Okay, so we've learned about derivatives. We've applied it to chapter 1 with the chart and increasing, decreasing. We learned this long way, the definition of derivative. We've learned some shortcuts. We've investigated limits. Okay, And we've done this thing with the powers. Okay, section 6 is going to say, okay, let's take all that same stuff and let's apply it to exponential and log functions. Okay? And then section 7 is going to say, let's take all that stuff and apply it to the trig functions. All right, so that's what 6 and 7 are about. They're the exponential, log, and the trig function. So what we're going to learn today are some shortcuts for the rest of the trig functions and log and so forth. Okay? Section 5 is kind of a standalone section that is about kind of a new thing, and that's what we're going to focus on tomorrow and Friday, and probably a lot of Monday as well. Okay, and it's kind of a separate thing that's out there a little bit. It's related to trig and exponential functions, and it's related to derivatives, so it does have a connection to all this, but it's also kind of new and different as well. So what we're going to do is we're just going to focus on the rest of these functions we haven't talked about. Okay, so let's do this function, b to the x power. In other words, what happens if it's not e to the x? What happens if it's 2 to the x, or 3 to the x, or something like that, some other base? Again, the key though is the x is in the power. This is not a power rule. We do not bring the x down in front, ever, ever, ever. Now, I say ever, we did it in this log, but that was different. For a derivative, we never bring the x down in front. One of the rules of logs is when you have the log of something to a power, you can bring that power down in front. That's a whole different thing. That's not doing a derivative, that's just a property of logs. Okay? When you're doing a derivative, we don't do that. This rule is only for x raised to a number. Okay? This is a number raised to an x. It's a different family of functions. It's called an exponential function. All right, well, here's the derivative rule. Okay, very similar to e to the x. That the derivative of b to the x is b to the x, but times an additional multiplier, ln b. Whatever the base is, you have to tack on an ln b. So if this was 2 to the x, the derivative would be 2 to the x times ln 2. If this was 3 to the x, it would be 3 to the x times ln 3. And so forth. Now, ln2 and ln3 are just numbers, okay? So the lesson to learn from this is it's almost the same as this. Matter of fact, it really is the same because according to this rule, this should be e to the x times ln e. What's ln e? 1. So really, this rule would be enough. We wouldn't need this rule in between here, except the e function happens so often that we do. But really, this function, this rule covers it. Okay, and so ln e is just 1, and so we don't even put it in. Okay, so derivative e to the x is e to the x. Derivative of any other thing to the x is that thing to the x, and then tack on ln of the base. Okay, so let's do a quick example next to that one. So let's say let's combine some of the other rules we've just talked about. So if we were going to do the derivative of 4 times 2 to the x minus 1. Now, first of all, you can't take the 4 times the 2 and make 8 because exponents take precedence over multiplication. Please excuse my darn self. You cannot combine them, okay? So what did we learn? Well, we learned when you had a a number out in front, what happens to it? It just stays there, right? Hangs out. What is this? What's the derivative of this? Well, that's this rule. Now, what's the minus 1 do? That's a shift. It's on the inside. The inside always stays the same. The shift doesn't affect our slopes other than moves where they are. So the inside stays the same. So what's the derivative of 2 to the x minus 1? 2 to the x minus 1 times natural log of 2. Okay, because we're just following this rule, along with 2 of our earlier rules. One of our earlier rules said you got a number in front, it just hangs out there. You got an x minus 1 on the inside, it's just going to stay an x minus 1 when you do the derivative. So basically this is just doing 2 to the x. You got 2 to the x, that derivative is 2 to the x, tack on an ln2. There it would be. Now if you want to move that ln2 around front and put it with the 4, you can, but that's just rearranging. I don't really care about rearranging. It's not necessary. Sometimes it's nice. What if we had to do the second derivative? Might be nice to have the 4 and the ln2 around in front, right? If we had to do the second derivative, what would happen? 4 ln2 is a number, it would just hang out there. Derivative of this would be this times another ln2, right? You have another ln2 tacked on, right? So we want to be able to put these rules together and be able to do these derivatives. So there's just an example on that. Okay, so that's exponentials. Next one. Let's move on to the logs. Okay? So if we have the derivative of a log, base b, okay? Derivative of a log function. Now this is kind of an unusual one. We've just noticed that when we have a power, when we do the derivative, we get another power. So if you have an x to the fourth, the derivative is x to the third. It's in the same family, right? We just saw that if you have an exponential function, the derivative is another exponential function. It's in the same family. And we saw the derivative of sine is cosine, right? We're going to write that one up here a little bit. Again, stays in the same family. The only time that doesn't happen is when you do a log. The derivative of log x is 1 over x. You don't get another log. Now, you do get a number multiplier, just like you did with the exponential we just did. It's 1 over ln of the base. But that's not really a log, that's just a number, right? ln b is just a number. The function changes from a log function to really a power function. That's x to the -1, actually. Okay? But that's the derivative of a log. You just have to remember that. So now what if this would have been log 3x in here? We'd add 1 over 3x. Remember we said the inside stays the same? Well, this thing is the inside, and it goes down on the bottom. So if you've got 3x on the inside, what if this would have been log of x minus 1? You'd add 1 over x minus 1, right? That's when so we say the inside stays the same. It doesn't seem to be inside anymore, but that's where it goes. Okay, with sine, with those other ones, it's kind of more obvious. Okay, and then we tack on this, 1 over ln b. Okay, now what about natural log, which is the one we'll see most of the time? Well, it should have that same rule. 1 over x, and then what would the multiplier be? 1 over ln e. What's ln e? 1. So you actually don't write. So when we do natural log, so when we do the derivative of natural log, it's just 1 over x. So if this was ln x minus 1, it'd just be 1 over x minus 1. Okay? And with no multiplier. Just like e to the x doesn't really have a multiplier, it's just a multiplier of 1. All right. So those are the log rules. Finally, section 7 are the trig rules. So we already know derivative of sine, and that is cosine. So the next one would be, that would make sense, would be derivative of cosine. What is that? Close. Now, if you remember when we did the sine one, we actually graphed its slopes, didn't we? So here was sine, right? Here was a sine function. You don't have to write this down, just do it. So the slopes start out as a 1, but get less. So we plotted 1 and getting less until they were finally 0. Then they're negative and get more negative. Then they start getting less negative, right? And we're like, oh, hey, that's cosine. Well, let's try it if you started with cosine. Right? If you started with cosine, the slopes start out 0 but are negative right away. So they start here and go here. Now they're negative, get more negative. Then they're getting less negative. Then they're positive, and it's going to do that. What's that look like? Looks like negative sine x. And that's exactly what it is. Cosine, the derivative is negative sine x. So we just have to memorize it. Okay? Derivative of tangent. x is secant squared x. Just have to memorize that. Secant squared. Kind of makes sense it'd be squared because if you think of the tangent curve, it kind of goes up like this, kind of like cubics. It's a whole bunch of those. It's always positive, right? The tangent graph is always positive slopes, I mean. So it makes sense that its derivative would be a square. And then cotangent, we kind of pair these together. It makes them easier to memorize. The derivative of cotangent is negative cosecant squared. So if you can memorize tangent, it's pretty easy to memorize cotangent. Matter of fact, you start to notice a little bit of a pattern here. Sine was this derivative. Cosine was negative. Tangent is this derivative. Cotangent is negative. Very similar, but negative. Okay, so they're called the cofunctions. Sine and cosine are cofunctions. Tangent, cotangent are cofunctions of each other. And secant and cosecant, same thing. So let's finish up those last two, so you could probably kind of guess these a little bit once you see the first one. So the derivative of secant x is secant x tangent x. Derivative of secant x is secant x times tangent x. And so the derivative of cosecant is, what do you suppose? Negative cosecant x cotangent. So that all the cofunctions, cosine, cotangent, cosecant are negative. Sine, tangent, and secant are positive, and then, or don't have a negative on them, but okay, and that's it. We just kind of have to memorize it. And then we could, you know, put some of those in combination. All right, so that's, we're going to leave it with that. There's some other stuff in here. There's some chart problems, some things like that, but those are some things we'll get into a little bit later on. So if, let's just do an example. Let me pull up an example here of one problem, and then we'll let you work on some of these and see about some of the, let me see here, I gotta think, quiz. All right, so let's do, let me work kind of, let me leave myself a little space, you know where I'm going to go with this. Let's let f of x be x cubed minus sine 2x plus three to the 4x. Find f prime of x. You just did. All right. Everybody get that right there? Don't look if you don't want to yet. Right? If you don't want to see it yet, don't look. Got to kick out a 4 on that last one, right? That's that other rule, right? We got to kick out a 4. And the rule also, the exponential rule of bases other than e says you got to kick out ln of the base, ln3. I mean, that's just the rule. If that was e to the 4x, we just would have had e to the 4x times 4. Right? The ln e would just be 1. Now you can leave it that last one like that, or you could take the 4 and the ln3 and move it around in front, but there's no real reason to do that. Again, that's just rearranging. All right. Now do f double prime.
Ay, ay, ay.
Now I've got the first 2 terms up here, not the third, so if you want to check those, maybe. We good there? It turns to a positive, right?
I did that part right. I really think I switched.
Because the derivative of cosine is negative sine. The derivative of cosine is negative sine, so it would 2 negatives would make a positive. You kick out a 2 again, which would give you the 4. This 2 in front, this 2 in front would just stay there. Kick out another 2. Okay. Now let's talk about this. This right here is just a number, right? And we always said if you have a number in front of a function, it just sits there. Well, this number's not in front, it's behind, it's the same thing, right? We can move it around in front if that makes more sense. So if it's 4 ln 3 and then times 3 to the 4x. So what you have is a number times a function. So that number just sits there, 4 ln 3. And now we're just focused on this, right? We're just doing the derivative of that, which is 3 to the 4x times 4 times ln 3. That's right. So this 4 times ln 3 that was there was just a number setting in front, like this 2. It just stays there. Derivative of 3 to the 4x is 3 to the 4x. Kick out a 4, just like we kicked out this 2. And the rule says when you do 3 to the 4x, you got to tack on ln 3. Now, could I rearrange those? I definitely should put 4 times 4 and write 16. I mean, simple, obvious simplifying. And we'll talk more about this when we get in chapter 3. We should do. Now, ln 3 times ln 3, that'd be ln of 3 quantity squared. Or if you just want to write ln 3 twice, that's okay too. There's no other real good way to simplify that. And then the 3 to the 4x. Okay? Very good.
I like this stuff.
Yes?
When we go from F prime to F double prime, and F prime has to do with more F,
Right?
we don't do anything. That's like what you choose to do, not what you're.
I'm not sure I'm following.
Like, why don't we do anything?
With this? Well, we did. Okay, here's f. We started with just this. And then its derivative was this. Now we're going to f double prime, so we need to do the derivative of this. Okay? Well, these two pieces are just numbers. And so they're just sitting there like this 2 is just sitting there. So this 2 just sat there. We did the derivative of that, which would be negative 2 sine 2x. Now, once I put that negative 2 with that negative 2, that's why I turned to plus 4. So over here, this is just going to sit there, which is what this is. And then we're going to do the derivative of that, which is just like when we did the derivative of that. So it's not, we're not doing anything to it. We are. The derivative of this then is all of this. Does that make sense? And then we just put it all together then. Okay? All right, now, do big F of x. The antiderivative.
It sounds so ominous. because-
Remember, like the dark side or something. Okay, so big F of x. Remember, its antiderivative is kind of a little bit doing opposite. There's kind of that phase to it. It's kind of a guess and check kind of a thing, that you write down what you think maybe would be reasonable and then check it by doing the derivative. And when you do the derivative, if something's missing, you can tweak it. Okay? It's not really just following a rule as much as it is kind of taking the rule in reverse, guess and check a little. Okay, I got the first one up here. We okay with that? We get the first part?
Can I do the next one? And then the part after that.
Okay, to me that's the first part. Now, so the next part I'm kind of going in reverse. So what sign, what's a good guess is what's going to have to be here? Cosine. Right? Well, okay, right. But you're a little ahead of me on the half, but definitely cosine, because the derivative of cosine is sine, but the derivative of cosine is negative sine, right? So I'm going to want this to be a plus, right? Derivative of cosine will be negative sine. That'll take care of negative. Now, what did we say about the inside? Those always stay the same, right? So that had to be a 2x. But when here's the guess and check part. When you do the derivative of cosine, you get negative sine 2x, but you got to kick out a 2. There's no 2 there. So there must have been a 1/2 setting here, because I know I have to kick out a 2. So when I do this derivative and I kick out the 2, it cancels with the 1/2, and that's why there's no 2 on that one. So I need a 1/2 out there. Okay, and it could be on the back end too if you want it over there. Usually we'd put that in front. All right? Plus, and now the same thing is going to be true here. What would be a good guess, or at least a starting point, that the derivative is going to, or the antiderivative is going to have in it? Doesn't it have to have a 3 to the 4x in it? I mean, look at all the f prime and f double prime we did. Every one of those had a 3 to the 4x in it, because the rule says we do the derivative of 3 to the 4x, it's going to be 3 to the 4x, and then you've got these additional things you have to kick out or whatever. So it's definitely going to have that. So what I would do is just start with that and say, let's just pretend it was that. Well, if it was that, when we do the derivative, what's going to happen? We're going to have, there should be a 4 sticking out here and an ln3, but they're not. So what's that mean? There must have been a 1/4 to cancel that 4, and there must have been a 1 over ln3 that caused the ln3 to cancel. And remember, 1/4 and 1 over ln3 are just numbers, and so when you have a number just setting next to a function, it just stays there. So when we do this derivative, these would have just stayed there. We'd have done the derivative of this, we'd have kicked out a 4, which would have canceled that, and we'd have kicked out an ln3, which would have canceled that, and we'd have had that. And then don't forget the plus C, right? When you're doing an antiderivative, there could be some constant there that when we did its derivative just disappeared. Okay? All right, now, on this next quiz, there'll be a little bit with this antiderivative idea, but not a lot. The main focus will be the derivative one. All right, so for your homework, today, for tomorrow, we're going to do, and you got the rest of the time to work on this, on your assignment sheet, everything else. Okay? That section right there, 2.6, 2.7, the one right above the solving equations review sheet. A little out of order there. Okay, now most of these, listen, most of these, like 16 through 30 even, what those are, like 16, they give you a F, and then the next section they give you, do the F prime of that, the next section they say do the F double prime, and the next section they say do the antiderivative of that, right? I mean, so you'll see, I think we did that in one of the other assignments too. Yeah, maybe we did. But anyway, so that's like the 16 through 30 even, 18 through 34 even are those. Okay?
E for even.
Yes.
E for evil.
So as you're getting started there,
If there was an A, B, C, or D.
okay? So I'm going to jot down a couple of notes to help you get started here as you look in your book here. So what's that with the evens? You got now. Oh, great question. They're evens, you can't check them back, but your calculator, you can check them. You can do the derivative on your calculator, right? You can check them.
How do you do that for them?
I'll show you that here in a second. So just so we don't get real hung up with something that should be kind of easy. Number 6, they give you this, and then they say use theorem 12 and use theorem 11. Well, those are just the derivative rules. Okay, so when they say use theorem 12, use theorem 11, you look back in the book at what those theorems are. They're just the derivative rules that we just wrote down. Okay, so that just means use the derivative rules. So then they ask you for h prime of several things. Like one of them is they ask for h prime of 1, for example. What's h prime of 1? Well, what would you do to find h prime of 1? Do h prime of x, right? Follow the rule to do h prime of x and then plug a 1 in for x. It's that simple. So what would be the derivative of this? What's the rule for log? 1 over x, 1 over ln 10. So then you'd put a 1 in for x. 1 over 1 is 1 times 1 over ln. I mean, it's that simple. It's just, you want to find h prime of 1, first find h prime of x using your rule, plug into it, okay? And then the rest of the homework is pretty much just doing derivatives, just using these rules. Okay, number 10, on the next section, this page 147, says g of x equals x plus sine x. So I just want to give you enough to get you over the hump of getting started. And it says on 10, does G have any stationary points? That's part A. Or no, that's number 10. Does G have any stationary points? Where do you look for stationary points? Where the derivative has zeros. So you're going to do G prime. So notice how this is just like what we did on the quiz yesterday, just like we did in the earlier section, except we have a trig function that we know how to deal with. So G prime would be what? 1. Well, it'd be plus, I think, right? Derivative of sine is cosine, positive. And then equals 0, right? We would have 1 plus cosine x equals 0. Now we need to solve this. Well, you can see where that worksheet came in that we were doing today. We've got to be able to solve this trig equation. Where does cosine equal -1? Well, cosine graph would tell you it's at pi. The unit circle would also tell you it's over here at pi. Cosine equals -1. But notice in this problem, we're supposed to look from -5 to 5. So cosine would also, if you look at the cosine graph, would also equal it back here at -pi as well. So we've got to look at what interval they've given us. So on problem 10, they told us to look between -5 and 5. So those are our two stationary points. Now, we would, if we wanted to do local max min, that kind of stuff, then we would put those on a number line, right? And we would just do all that same stuff we did, you know, when we were doing polynomials. It's the same thing. So those are our stationary points. So that answers question 10. You can skip 11 for right now. It does inflection points. We'll talk about that later. So you can skip 11 on that little section for right now. So that's 10. I think 11 asks for local max and local min. 11 and 12, or 12 and 13. 12 and 13 asks for local max and local min. So now you can do your number line and you can go from there, okay? And then we'll be working a lot on that next couple days, especially with the trig. All right, the rest of the time's yours. Yeah, you can too. That's fine. Yes, you may.
Have you seen that vibe?
Okay, so some of you are going to be gone Thursday, Friday, right? Yes. You do, because I do. Well, as much as I like hearing that, yeah, we'll put them up. I mean, and we'll visit when you get back. I mean, if it's like, God, there's no way we can do this quiz, we can do it after Thanksgiving. Yeah, yeah, that would probably not be an option. But you're right. There's no other good options. Wait till after Thanksgiving, or just suck it up and get it done. So, try to get ready. I'll have the videos and stuff up there.